What I'm going to describe here today is the next project, which is finding your way through a maze. And in this, I'm using Harry Potter, is that you're at the start of the maze and you're trying to look for the Horcrux, which is the X there. Now, it's very important that when we do this, that when we go and look for neighbors, which I'll explain, we go in the following direction. We always are going to check east, then we're going to check west, then we're going to check south, and then we're going to check north. What I'm going to explain to you in this video is what this means, and for this right now is the stack solution. There's two different ways to solve this, and one's called a breadth first and one's called a depth first. A depth first means that we use two stacks, and that's what I'm going to show you. One stack represents the solution. The other stack represents the neighbors. This stack is always going to change, meaning that I'm always going to get new neighbors. This stack is always going to basically get more inside of here. What this is going to have at the end is the solution. So what I do is, in our project is we're always going to start at 1, 0. So if I start at 1, 0, so I say what I want to do is I want to have a current space. And that current space right now is going to equal 1, 0. With the current space is I am going to check to see if it's visited. If it's not visited, I'm going to push on the solution stack. So in this case here, I'm going to take my 1, 0 and put it on my solution stack. I am then going to get neighbors. Now with the get neighbors, this is where I was talking about. You want to always go in this direction. So you always want to check to the east. So here's 1, 1. When you find out there is a neighbor, you put it on the neighbor stack. Then you check to the west. Here, this is out of bounds. I check to the south. Well, it's a wall. And I check to the north. So the only valid neighbor I have is 1, 1. There's going to be more code here, but right now what happens is that my 1, 1 becomes my current space. So this here basically loops back up here and it checks the next one. So when I check to see if 1, 1 has been visited, it hasn't, I mark it visited, mark visited. I mark it visited and I push on the solution stack. Once again, I'm going to fill this in as we go. I'm come to the top. I get my neighbors. I'm at 1, 1. So here I'm at 1, 1. This is the first time this is going to play into this. So I want to go in the order east. So if I checked to the east, it's a wall, so I can't do anything there. If I check the south, yes, there's something there, and it has. The big thing is it hasn't been visited. So I'm going to say, okay, put 2, 1 on my neighbor stack. Then I check north, and it hasn't been visited, so that's 0, 1. I did have to check this area here. Right now I'm standing here. I did check west, but this was visited, so I don't put it on the stack. I don't want to repeat myself. I don't want to go in a circle. So what happens is after I get my neighbors, I find out how many neighbors. If I had 2 or more neighbors, I mark the current space as an intersection. And the reason I mark it as an intersection is because I'm going to use that for backtracking later on. So in addition to marking this one visited, I also put an I inside of there. So now I have to decide which of these 2 neighbors to pull. Well, all I do is pull the top neighbor. So here, when I take 0, 1 becomes my next current space, But also at the same time, this neighbor stack is zeroed out. Next time I go over here, I gotta get new neighbors. So 0, 1 is my current space. So that means that I check to see if it's visited. It hasn't been visited. So I move my guy up here. I mark it visited and I put it on my solution stack. Now here I'm gonna get neighbors again. Now when I go to neighbors, I'm gonna check east, it's a wall, west, it's a wall. I'm gonna check south. However, the south is already visited, so I don't wanna put it on my neighbors because I don't wanna go in a circle. And I check north. So here comes the next one. So I had a case if I had 2 or more neighbors. Now, if I have 0 neighbors. If I have 0 neighbors, I want to backtrack. Backtracking means that I'm going back to an intersection point. Now, in this case, I'm only going back 1, but let's say this went further down and I got my guy all the way here. Well, it would backtrack to this point here. So I would backtrack by popping this off, going here. Is this an intersection point? No. Popping it off, going here. Is this an intersection point? No. Popping it off, going here. Is this an intersection point? No. Popping it off. So it doesn't matter. I could go back 1 or I can go back 50. It doesn't really make a difference. What I'm trying to do here is I'm trying to pop off the solution stack the dead end. So I pop to an intersection point. So I look at 0, 1, that's where I'm at the dead end. I pop it off and I throw it away. In this case, I come back to 1, 1, which happens to be an intersection point. So backtracking means pop off until I reach an intersection. So once I backtrack and I get to a point where I have an intersection, I go back and that becomes my new current space. I have 1, 1, that's my new space. I then go get I check to see if it's been visited. It has, so I'm not gonna push it back onto the stack, it's already there. I'm gonna mark it, I don't have to mark it visited. So if it hasn't, been, check to see if it's visited, okay, I'm come here. So what I have going on is that if it's visited, also, I get my neighbors. And this is because I have to go back and do the same thing. So here I get my neighbors. And what I'm going to do is I go east, wall, west, been there, south, haven't been there. So I'm going to put a 2, 1 inside of here. I go north, I've already been visited, and now it's time to move on. So I did get neighbors for if it's not visited and visited. The thing is if I get to the point, either one of these locations, if I get to visit it and I have no place else to go, that means that if I have no more visited, so if I have no more to visit here, that means the maze is not solvable. But in this case, I do have more to go. So what I'm going to do is I'm going to now put 2, 1 as my next current space. Put it inside of here. And if I get here, I check to see if it's been visited. It hasn't. Mark it as visited. Get the neighbors. So I'm going to come. So now I'm sitting here. Go in the same order. Check east, wall. Check west, wall. South. It's a valid and it hasn't been visited. So I'm going to put 3, 1. Check north. Well, it's been visited, so I'm not going to put it on there. So that means I come back up here. I put in 3, 1. Is my next one that comes on here. Has 3, 1 been visited? No. So I'm going to move there. I'm going to mark it visited. And I'm going to check for neighbors. I'm going to go east. Yes, I have east, so 3, 2. I'm going to check west. I have 3, 0. What becomes the next one I do is 3, 0. Even that we can see 3, 0 is the wrong way to go, the program's not looking at this map that we have inside of there. So we are going to go in the wrong direction. So we're going to push 3, 0 on here. And when we come here, we check to see if it's been visited. No, it hasn't, so I'm going to move there. I'm going to push it onto the stack, and I'm going to get the neighbors. Now, when I come here and try to get neighbors, I go east. We've already been there. West is out of bounds. South is out of bounds. North is a wall. So I'm at a dead end. So I'm going to say here, I have no neighbors. I'm going to backtrack. So what I'm going to do is I'm going to backtrack to the point of, so I'm going to take 3, 0. I'm going to look at 3, 1. Great. 3, oh, I should have marked that as an intersection. I'm at 3, 1. That was an intersection. So now that becomes the next. Well, it has, okay, so check to see if visited. It has been visited, but I'm going to try to get neighbors. If I can't get any neighbors this time, then that means I'm at a dead end. And it also means that there's no solution. So here, what I'm going to do instead is I check to see if there's, get neighbors. I try to look east. I put 3, 2 in the stack. I look west, that's been visited already. I look south, that's out of bounds. I look north, I've already been there. So I push, at 3, 2 becomes the next current space. Has it been visited? No. I push on the solution stack. Now, there's one other thing. So here, I also have to check, is it the exit? If it's the exit, stop the algorithm. Because I have the solution inside of the year. So now, even that I visited every single empty spot in this grid, the solution actually is if we pop this stack, the solution is I have here, 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 and here. So the solution is actually only this. While we went to every single spot, this is the solution for this one here. So in the end, I'm only going to print out these places here. The algorithm basically went through and tried to find if there was a solution or not, and it found a solution. The other way to do this, if I empty out my whole entire grid again, and I still have the same entrance point, if I still have the same entrance point, is to change how I do this. Instead of using a stack for the neighbors, what I can do is use a queue for the neighbors. So what happens here is this is called a breadth first search. And this is like branching out. You have a start point and you have a group of 4 people. Well, 2 people go this way and 2 people go this way. And then let's say there's another intersection point. Well, 1 person goes this way and 1 person goes this way. At the same time, if this one keeps on going, we just keep on following that down. So here, what we're going to do is instead of going one path all the way and seeing if it's the exit, and then backtracking, here we're going to fan out and try to get the solution. So what we do here is we use 2 queues, but it's the same exact algorithm. So if we were to start here, what we do is we have our solution queue, and we have our neighbor queue. We come here, we basically mark it visited. Has it been visited? No. So our current, we say current space equals 0, 1. Has it been visited? No, it hasn't. Let's put it in the solution. Let's put it in the solution queue. Actually, sorry, this is 1, 0. Has it been visited? No. Let's put it into our solution queue. Now we have our neighbor here. We go and find our neighbors. Now the difference between this algorithm and the last algorithm, the only difference is that this queue never gets wiped out. it gets, basically you add on to it every single time. That is the only difference between the two algorithms in sense of how we use these data structures. So when I come here, I'm going to look for my neighbors. I'm going to use the same thing. I'm going to check east first. So east, yep, I have a neighbor to the east. So I'm going to put 1, 1 inside of there. I look west, it's out of bounds. I look south, it's a wall. I look north. So now what I do is my next current space is 1, 1. So that means I move over. I see if it's been visited. It hasn't, so I mark it visited, and I get neighbors. Once again, now the way we calculate how many neighbors there was before, so you have to keep track of before get neighbors and after get neighbors. And the reason why you have to keep track of the size of the queue before and after is because you have to know, is this a dead end? Is this an intersection point? What is this? So I still need to know some of these things. So inside of here, what I'm going to do is I'm going to mark this as an intersection point. And I'm going to get my neighbors. So I'm going to go east, it's a wall. I'm going to go west, I've already been visited there, so don't do that one. Go south, south it hasn't been visited, so I'm going to now, so that's my current space. South means that I'm going to get 2, 1, comes inside the queue. I am going to go north, and it's going to be 0, 1. Now, right away, you're going to see a difference because when we did the stack approach, 0, 1 was on the top of the stack. So that's the next place we went. Well, here, that's not the next place that we're going to go. Well, the next place we're going to go is at the front of the stack, which is 2, 1. So already there's a difference. We went to 0, 1 when it was the top of the stack, but now we're using a queue for our neighbors. So that means we're going to 2, 1. So after 1, 1, the next current space is going to be 2, 1. So that means that I'm sending part of my group here. Remember, this solution means that we're going to branch out. So what it's going to look like is when we were at 1, 0, I wasn't at an intersection point, so we went straight forward. Well, then I got to 1, 1, and we're at an intersection point. So the first set of people I sent, I want them to go down the path of 2, 1 to see if they can find the Horcrux by going down this path. Now when I go to 2, 1, yes, I have to get neighbors. So I'm going to do that. So the front of my queue now is 0, 1, because it's still in there. As I said, that's one of the major differences between the two algorithms, is that I'm going to get the neighbors. So I'm here right now. But really, somebody's standing right here saying, I'm only sending part of the group down that way. So at 0, 1, go east, wall, west, wall, south, okay, that one's open, so I'm going to go 3, 1. And north, I'm not going to put that in because it's already been visited. But notice the next current space, because remember, you always take it from the front of the queue. Now it's going to be 0, 1. 0, 1 hasn't been visited, so I'm going to put 0, 1 inside of here. So what that really means is, yes, I have somebody going down this way, but now I have a second person going this way to see, hey, maybe the solution's down that way. So I have somebody else going 0, 1. Now we can see on the board that it's a dead end, but the person standing back at 1, 1 doesn't know that it's a dead end. It might be a very long path. So what happens when I get here? Okay, I get my neighbors. So get neighbors, so 3, 1 still at the front. When I get here, I find out there's no neighbors, so I don't put anything inside of here. Okay. Great, I don't put anything inside, I don't care. What it says is that I still have no neighbors. I can't backtrack because this is a queue. Another difference is between the last algorithm and this algorithm is that one of the things that we have to track, because at the end of all this, we want to know what the real solution is that we have to know who the parents are. meaning that when we started at 1, 1, where did it come from? Well, I'm going to say it came from -1, -1, meaning that that was the starting location. Well, where did 1, 1 come from? Well, 1, 1 came from 1, 0. That's its parents. Where did 2, 1 come from? 2, 1 came from 1, 1. Where did 0, 1 come from? It also came from 1, 1. Now, what you may start to see is once I have the solution Q, the solution Q, unlike the stack, will have every place that we visited. What we will do after we find out is there a solution, we will play connect the dots going backwards with this. And I will describe that a little bit more in a few seconds. So I'm at 3, 1. That's the next available slot. Has it been visited? No. So I'm just going to ignore that 0, 1. Hey, I got to a dead end. So I'm now at 3, 1. Okay. I say market visit. So even that I had somebody up there, they went up that way and they figured out, hey, we're not going to go anymore because that's a dead end. So now I have my person still trying this way. So this guy here, I mark it visited. I get my neighbors. When I go east, east is going to be 3, 2. West is going to be 3, 0. South, out of bounds, north. Okay, so now I'm going to also mark this as an intersection point. Well, where did 3, 1 come from? That's another thing I need to remember. 3, 1 came from 2, 1. So I'm going to put down underneath 2, 1. So one of the things, I'm doing this afterwards, but when you put these in the queue, you're going to mark where it came from, meaning you want to mark the parent. So here I get my 3, 1. The next current space is 3, 2. 3, 2 is the, I take it hasn't been visited, I put it in my solution queue. Is it the exit? Yes. That's the end of the algorithm. I don't care that 3, 0 is still in there. We're never going to go to 3, 0. So now what happens is if we were to draw this as we went along, we had P, P, we sent half of our team that way. So then we sent part of our team this way. That's where we did the division. When we got to 2, 1, there was actually another division. So we put those in the queue, but we never went down this path. So this path went to 3, 0. We never got down this path because what happened was when we got to 2, 1, when we got to 2, 1, we went down straight. When we got to 2, 1, we went down straight to 3, 1. So we kept on our team going to 3, 1, so we have her there. At 3, 1, there was a division, so when we looked at the neighbors, there was a division. There was one that went to 3, 2, and one that went to 3, 0. We never got to this one here. We did get to this one here, and that was our exit. So these are all the points that we visited. So the graph would print out like this, but that's not the final solution. What we have in our solution queue is where we went everywhere. Now what we want to do is we want to actually find our solution queue by connecting the dots, meaning that we want to copy the solution and say, well, 1, 0. And I use a stack for this. So I said, okay, I push 1, 0. Okay, 1, 0. The next one is 1, 1. Is the parents 1, 0? Yes. Then I push it on a stack. This is just a temporary. I look at 1, 1, and I say, okay, the next one's 2, 1. Does 2, 1 have parents that it's on the top of this stack? Yes, it does. 1, 1 is the parents of 2, 1. So then I go to the next one. Basically, I'm dequeuing these as I go along. I get to 0, 1. The parents are 0, 1, the parents of 0, 1 are 1, 1. Is the top of the stack the parent? No. So that was a dead end. I throw that away. Now I go to 3, 1. Is the top of the stack the parent? Well, yes. 2, 1. Well, the parent is 2, 1. So I put 3, 1. I look at the front. I look at the queue. The only thing left inside the queue is the 3, 2. Is the parents the top of the stack? Yes. 3, 2. So now what I do is after I connected all the different things together, I put them back in the stack. So what do? Is I say 3, 2, 3, 1, 2, 1, 1, 1, and 1, 0. And now that contains my solution, and I can print out that it only did this. Now in this case, the stack solution and the Q solution were the same. That's not always going to be the case. The Q solution is always going to be the shortest path, meaning that if it only took 2 steps to get to the solution, but there's a 5-step solution, it's always going to find the 2-step solution. The stack, it's basically, it won't find one path, meaning that it may find the 5-step or the 2-step. It's not a unique path. Now, if there were 2 shortest paths, meaning that both took 2 steps, then that's a crapshoot. It's going to pick one or the other. So, if we look at the algorithms, they're pretty much the same. Breadth and depth, they're called. This one uses queues. This one uses stacks. We have a current space. Same with over here, current space. Has it been visited? Same thing. If it's not visited, we're going to mark visited, put in solution Q. Same over here. Mark visited, put in solution stack. Next thing we're going to do is get the neighbors. The difference between the 2 neighbors, this one uses a queue to get the neighbors. This one uses a stack. This one, it's important if we know the size. And this stack gets erased every time. This queue is maintained throughout. This, if it's 2 or more, mark an intersection. If it's 0 or more, if it's 0, we gotta backtrack. Here, it doesn't really matter if it's how many different. What we're going to do is we're going to take the next Q, front of Q becomes next space up here. Where does this end? Well, here, after this, here, if the current space is equal to the exit, this is a return true. Same thing over here. After we check it, we check here if exit, return true. Okay. Now, if this queue, if the neighbor queue in this solution ever becomes empty, and the current space is not not the exit, then return false. That means that there's no solution to this here. This one's a little bit different because remember that we clear out our stack every single time here. Basically, if we wind up backtracking, here, there's two different solutions. If we backtrack all the way to an empty solution stack, that's a return false. There's no path. The other way that this one here would fail is if you have an empty neighbor and the top is not the exit. At the end of this algorithm, the solution is the stack. In this one here, you have to create the solution. Once all of this is done. So that means when we're doing our neighbors, when we get our neighbors, we also get where the parent came from. So here parents are important. Here parents are important. Here the number of things that are on the neighbor stack are important. Here the things on the neighbor stack are not important unless it's empty. So those are the two different, basically, algorithms, and that's what you have to replicate.